Sound looks good. I think we're live. We're ready to go. Okay, so in front of you is today's lesson on continuity. I don't have to hand you another thing because tomorrow we actually won't do a new lesson. Tomorrow we'll kind of do I guess we'll call this a mid-unit review day. And we are quizzing the next time we see you, which will be Thursday. So tomorrow's class will be kind of a chance to just slow down, do some review. There's some exercises in the back of the big pink booklet that we can use as a review assignment. So that's why you only get one handout today. So today we're going to talk about continuity and look at these odd-looking things that you got introduced to in grade 11 called piecewise functions. We've seen a couple of them in this course so far. Give me a sec here to get organized. Yeah. Okay. All right, here we go. So, continuity. When we say that a function is continuous at x equals a, we mean that the function doesn't skip over x equals a, it doesn't jump from one place to another, or it doesn't stop existing at that point. Basically, we mean that a function is continuous at x equals a if you don't need to lift your pen off the page when drawing the graph at that point. And that is a very weak definition mathematically. So let's give you a formal definition. Function f is continuous at number a if the limit as x approaches a of f of x is equal to f of a. So, in other words, when I plug a in to the function, I should get the same value I get if I calculated its limit. And if that's true, then I'm continuous at that point. So here's example 1. Again, I think all the examples in this lesson are going to be piecewise functions. So where is the function discontinuous, and use the definition of continuity? Okay, so first of all, how did they make this function? Well, the function is the line negative x minus 2, but only when you are smaller or equal to negative 1. So starting at negative 1, it's this line here. So there's the first function. Then I'll use different colored highlighters here. Then it's just the function y equals x. Very simple diagonal line. But that only exists between negative 1 and 1. And please notice that there's no equal to's on these less than symbols, right? So, which makes sense because at the point x is negative 1, you can't belong to two different functions at the same time and still be overall a function, right? For every x, you have to have a unique y value. So starting infinitely close to negative 1. Remember, negative 1 belongs to the yellow function. And then going infinitely close but not reaching 1, there's the next equation. And then lastly, I have a quadratic, x squared minus 2x, but only when I start at 1 and go to infinity. And that's that part of the graph. Okay, so that's where this thing comes from. You will have some questions. Some of you probably already started them, right? Because I did assign 1.3 yesterday, and I put on the blog that, today's lesson also kind of covers 1.3. So don't panic if there was parts of 1.3 you don't know how to do yet yesterday. By the end of today's lesson, you should be fine. Okay, let me get rid of all these extra lines here. All right, so now let's answer the actual question. Hopefully now we understand the graph. You'll get a chance to try drawing some of these graphs yourself in the homework. But where is the following function discontinuous? Well, you can kind of see it if you just look at it visually. It's right here. This dotted line is just to show that those two things are vertically exactly over top of each other. It's not part of the graph, okay? Notice mine's blue. Yours, of course, is black and white. But the blue lines are the graph. That dotted black line is not part of the graph. And what it's trying to show you here is that we have what we call a jump continuity. All right, let me pause for O Canada here. And we're back. Okay, so these three equations together make one function. But is it a continuous function? The answer is no, because if I was tracing it with my pen, I would have to lift my pen up when I get to x is 1. So I will write down in kind of notey form here, f of x is discontinuous at x equals 1. And you have lots of room under here, so we're going to write down a bit of notes here, and this is going to say that there are 3 types of discontinuities. I think I've spelled that right. Discontinuities. Yeah, sure. So the 3 types of discontinuities are removable, jump, and infinite. And let's quickly define what those things mean. The one that we have here, you could probably guess. Guess which one we've got on our first example here. That's a jump continuity. And so let's talk about that one first. A jump continuity means as you approach x equals a from left and right, you approach 2 different values. So that's my jump discontinuity. Sorry that I'm writing kind of crooked there. Removable, we've seen lots of these. Removable is just an infinitely small hole in the function. And think about where we've seen these. We've seen these when we have something like a quadratic divided by a linear, where the quadratic has that linear as one of its factors. Right? There's only one single point. There's one single a value in the whole universe that the graph isn't defined for. So it's just one little hole. So we've seen quite a few of those. Infinite, we're not going to talk about much right now. Infinite discontinuities are when x approaches a from the left gets infinitely, and I just misspelled infinitely, infinitely far from x approaching a from the right. In other words, the closer you get to a from both directions, the further apart your y coordinates get. Any idea what kind of thing I'm describing? A good example of this would be, suppose I wanted the limit as x approached a, or sorry, as I didn't mean to put a, as x approached 0 of 1 over x. What happens when you get closer and closer to 0 for 1 over x? What kind of a thing are you talking about here? Yep. Sorry, let's say that again. You're going to have, yeah, you're going to have, not only are they different values from each side, the closer you get, they're going to be infinitely far apart. Again, what do we call something like that? In grade 11, you started off by calling them non-permissible values. And then you discuss them as a line, as a vertical line that you can't ever touch. What do you call that? This is asymptote land. So infinite discontinuities, so here's the 3 types again. Removable, oops, my pen stopped working. Removable, jump, and infinite are the three types of discontinuities, and this x equals 0 is a vertical asymptote. So there we go. So that's the three types of discontinuities. And as you can see, the one that we have on our example here is we have a jump discontinuity. It just sort of teleports from one value to the next as you're going along the line. All right, example 2. Where is the following function discontinuous for this one? And again, use the definition of continuity. So this is interesting. I follow this thing with my pen. If I trace it, if I trace this thing with my pen, I don't really have to lift my pen here, but it certainly does change direction. Direction changes don't count as discontinuities, but certainly when I get to this spot here at x equals 3, we have a jump discontinuity. So f of x is discontinuous at x equals 3. And of course, you wouldn't really be able to see this just by looking at the equations. I mean, you could run some algebra, right? You could say, all right, well, what happens if? So let's just write this down. How could I determine this without graphing? Well, because I'm going to take f of -1 and figure out what that is in the two parts of f of x that are bounded by -1. You know what? I think there's a mistake on here. From when x is smaller. This, you know what? This should be just a 1, not a -1. Can you fix that? Put a little positive on here. There we go. That's a mistake. Sorry about that. That should be a positive 1, not a -1. So how could I determine without graphing what kind of discontinuity I have? Pretend I didn't have this picture. So I'm going to try to figure out what f of 1 is in these two parts of my function. So let's find f of 1 in the first one. So I'll just kind of bifurcate this into two. So that's -1 squared plus 4, which as you can see is going to be 3. And then if I plug it into the other one, I get 1 plus 2, which is also 3. Therefore, it is definitely continuous. Even though I've switched from one equation to another, I didn't have to lift my pen because where one of them ends and the next one begins is the same value. But now let's try f of 3. Well, f of 3 would exist in the function x plus 2, which gives me 5. And f of 3 would exist in the function square root of x minus 3, so that's 3 minus 3. Okay, which is 0. And since these two values are not the same, therefore it is discontinuous. And you can definitely tell it's a jump from 5 to 0. That's an F, sorry. Having all kinds of problems with my pen today. All right, now, most of the questions we assign you like this, we actually do want you to think about the graph. And if it says make a sketch, then you can just make a little sketch of a graph. But I also encourage you to use Desmos. There is a way to do piecewise functions on Desmos. And I'm going to show you how to do that. So on Desmos, you can write this down if you want. Okay, Vittorio, can you mute? Thank you. On Desmos, okay, what do you have to do? You have to type it in as y, oh come on, pen, as y equals, and then you have to use these curly brackets that I'm so bad at drawing, condition, then you use a colon, a full colon, then the value, then comma, condition, full colon, value, comma, and then you could just say etc. So that's the way you have to type it in. You kind of have to type it in backwards of the way that you would look at it on paper. In other words, you have to put the domain restriction first. So this part here, of course, is the domain restriction, then a colon, and then the actual value of the equation. So if I wanted to put this into Desmos, I would do it like this. So let me get to Desmos here real quick. So okay, so I'm going to type in y, or I could type it in as f of x. It doesn't matter. So f of x equals, and then I need the curly bracket, which is right beside the letter P on your keyboard. So shift curly bracket, and then I have to put in the condition first. So I'll go x, and if you're looking for where less than or equal to is, you have to just go down here, and it's in the menu, less than or equal to, and then 1. Okay, and then colon, and then the actual equation, which was negative x squared plus 4. And there we go. So there's the first part. Then you put a comma, and then you just keep typing. So the next restriction is x has to be between 1 and 3. So I have to go 1 less than x less than 3. Oops, hang on. I didn't do that right. Less than, there we go. 3. Okay, and then colon. And then this was the equation x plus 2. There we go, there's the next part. And then comma, and then my last restriction is x is greater than or equal to 3. And colon, and then this is the square root. And square root, there, you can use square root off of this menu here, or if you actually just type in SQRT, it knows to make a square root. And then x minus 3, and there we go. There is the Desmos version of the graph that we were playing with. And as you can see, you definitely have a jump discontinuity. If you actually trace along, it'll go to the very end of this one, and then it'll like jump to that one as you trail to the right, which is kind of fun. So there we go. So that's how you can, if you're doing your homework and it's like, I'm not sure I have this graph right, you can plug it into Desmos and check to see if you've done it right. Okay? All right, moving on to the next example. What about absolute value functions? Okay, again, these you got introduced to towards the end of grade 11. And the square root of x minus, or sorry, the square root, the absolute value of x minus 2 would be just your basic absolute value graph shifted over 2 places to the right. So it would have a vertex here. Whoops, I am not on a pen. It would have a vertex here, and then it would go up 1 over 1, so it would go through that way. And then it would have an arm that goes this way as well. So there we go. So now, determine the limit as x approaches 2. And as you can see from this graph, you're actually, if you approach it from the left, remember how we defined limits the other day, that if the limit as you approach it from the left and right is the same, then you know that that's what the limit is going to end up being. So the limit as x approaches 2 from the left, well, let's see, as I approach 2 from the left, as I'm going that way, it looks like I'm heading towards 0, right? And the limit as I approach from the right also seems to be equal to 0, because again, if I approach from this way, I'm heading towards 0. So, oops. There we go. So therefore, the limit overall as x approaches 2 of that is equal to 0. Okay. So that's a pretty straightforward one. But these get more complicated when there's more pieces on them. So this one's kind of fun. What do you think of example 4? I don't know why we gave you so much room for example 3. I don't need any more room for that one. But check out example 4. We've got an absolute value on the top, and then we divide on the bottom by the actual same factor that's in the absolute value bracket. What do you think that's going to look like? Okay. Well, let's see. First of all, maybe a good idea would be to think about what would happen if this thing, what if it was the almost same looking function, but it wasn't an absolute value bracket? So there we go. Think about what y equals x minus 1 over x minus 1 would look like. Well, what's anything divided by itself? It's just going to be 1, right? But there would be a removable discontinuity in it, right? There would be one spot where this graph couldn't exist. X couldn't actually be 1. So it would be, if I were to sketch it, it would be, there's the y-axis. There's, oh, let me try that again. That's very crooked. There we go. Oh, a little better. There's the x-axis. And it would be a graph, here I'll draw it in blue. It would be a graph of 1, but it would have an actual hole at the value x equals 1, right? Does everybody get that that's what it must look like? Okay, with that in mind, what does the absolute value change about that? Well, notice an absolute value means that you can't get a negative in the numerator. So if I plugged in, let's plug in some values. If I plugged in 0, I would get 0 minus 1 is negative 1, but the absolute value of that makes that 1, but that's 1 divided by negative 1. So at 0, looks like we're going to be at negative 1. What happens at negative 1? Well, the numerator would be 2, but the denominator would be negative 2, so we'd still be at negative 1. So we're going to go this way. But what happens to the other direction? So let's think about that. What happens if you plug in positives? Well, first of all, can you plug in 1? No. So once again, 1 is not going to exist. But what happens at, say, a half? What happens between 0 and 1? So let's plug in a half. So let's make a little table of values here. So we've tried, what did we try? We tried 0 first and we ended up getting negative 1. We tried negative 1 and we got negative 1. We tried negative 2 and we got negative 1. Right? What happens if we plugged in negative, or let's say positive 1/2? Well, the top is going to be a half and the bottom is going to be negative a half. Looks like we're still negative 1. So it looks like we're going to be negative 1 right up until we get to this hole. And then what happens when we start plugging in numbers that are bigger than 1? Like, okay, let's say what happens when we plug in 2. Good morning.
Have a great day.
Thank you. So what happens when you plug in a 2? It's going to be a jump, isn't it? It's going to jump up to 1. But once again, it's going to be a hole. So there we go. So the limit, what do I say about the limit here? Well, I can say that the limit as x approaches 1 from the left of this function looks like it's heading towards, well, it's definitely a y value of -1. And I can say that the limit as x approaches 1 from the right of this function is +1. So if the left limit and the right limit don't equal each other, what do you say? It's discontinuous, and therefore the limit overall of this function does not exist. Okay, we're going to just jump back to example 3. Actually, I forgot there is one more thing we want to do with example 3. That's why we have so much room. And we'll do it with example 4 too, but let's do example 3 first. You did this in grade 11. Can you express this function in piecewise notation? So how would I describe this function in piecewise notation? So first of all, is it called f? I'm going to call it f. F of x is, and do you remember doing this in grade 11? This is just grade 11 review at this point. If I'm not allowed, basically, how could I make that graph if I wasn't allowed to use the absolute value function? Okay, so this line here is the opposite of x minus 2. And that would be how much it is when x is less than or equal to 2. Then the other part of this function is the equation x minus 2 when x is greater than 2. And again, make sure only one of those things has an equal to on it, because the function can't be two different equations at the same time. Or the x values can't belong to two different equations at the same time. Okay, so now see if you can do that for the second one, for example 4. What does this thing look like in piecewise notation? And feel free to simplify it too. What does that function look like in piecewise notation? And again, you can simplify it. Okay, did you get that it's -1 from everywhere starting, but not including x is 1? And it's +1 when x is greater than 1. And now that you see it in piecewise, you can totally see the discontinuity, right? Notice that because neither of these two things have an equals on them, it can't exist at the point 1, therefore it's discontinuous at 1. Notice I didn't have that problem in the last one. In the last one, this and this tells me that it's continuous. I don't have to lift my pen. I got to change direction when I get to 2. It's where the bottom of the V is. But I don't have to lift my pen. It is continuous. So that's the basics on continuity and discontinuity. So we're not assigning anything new today. But if there is people who actually did plow through the assignment yesterday, even though I hadn't really talked about continuity until today, at least not much, I will go to the blog and I'll put up the review questions that you can start working on today that I'll assign for tomorrow. Okay? So, and then tomorrow's class will just be a chance for you guys to ask questions or just work time. I think you still should log in on Teams, okay, and then make sure, because, make sure that there's no questions that come up that you need to ask or discuss. So I'll still do the Teams kind of check-in with you. But otherwise, that's as far as we're going to go before our first assessment. Okay? All right, let me close off my video here.